Okay, Tomasz and his presentation about F#. Let's get started.
Hi everyone. So my name is Tomasz Heimowski, and I'm a software engineer at a company called IHS Markit. And here's my website and Twitter handle. And I'm going to talk about F# today. So I like functional programming and F# in general. So I thought I could share some thoughts with you. And here's the agenda of my presentation today. So first, I'd like to talk briefly about the history of F#. Then I'll go to the basics, and I'll make a comparison with SCALA. And then we'll go through the outstanding F# features. And at the end, I'd like to talk about the evolution of the language nowadays. Okay, so brief history. I go through such points such as what is F#, what were the origins of the language, and what were the other languages that influenced F# and influence right now. So, and by the way, this is the original logo, which was not probably that nice. And nowadays, this is the F# logo, which was chosen by the community, and there was voting. And so what is F#? And I quote fsharp.org here. So F# is a mature, open source, cross-platform functional first programming language. It empowers users and organizations to tackle complex computing problems with simple, maintainable, and robust codes. And I deliberately emphasized the adjectives here because I think this is the case. This is really the case for F#. So it's a mature, so it has a couple of years right now, and it can be used in production, actually. So it's open source, which is nice, as we all know. We all love open source projects, and it's cross-platform, which is quite crucial because probably someone who hears about F# and knows that's a Microsoft initiative might think that it's only limited to Windows and .NET, and that's not the case because you can write F# cross-platform. You can use macOS and Linux, and I'll talk more about that in later course. It's functional first, so it's not like Haskell purely functional, but it's functional first. And here's also pretty important adjectives. That's simple, maintainable, and robust. So the syntax is quite concise, and it's easy to understand the code. And it's really nice and easy to maintain, even large code bases in F#. Okay, so what were the origins of F#? And it was a Microsoft research initiative, and it was born in 2005, and actually was bundled with Visual Studio 2005. And there was this guy called Don Syme, and you can think of Don Syme as Martin Odersky for F#, and he led the development of F# from the beginning, and he's involved in developing F# right now as well. And F# aimed to incorporate functional programming on top of the .NET platform. And originally, they wanted to create a purely functional language on top of .NET platform. But based on the nature of .NET platform, it turned out quite impossible. So they decided to come up with a non-purely functional language. And what's interesting is that they've been strongly influenced by the Haskell. There was this guy, Simon Peyton-Jones and Simon Marlowe, which worked door-to-door with Microsoft research. They worked in Microsoft research in Cambridge, door-to-door with the F# team. And they had good contact. And so the influence of Haskell ideas were strongly visible in F#. And originally, F# was closed source, which is not longer the case. Influencing languages. Apart from Haskell, which I already mentioned, this functional stuff from Haskell, there's very much, a big influence of OCaml language, because the whole syntax in F# is very similar to OCaml. And if you can read OCaml, you can probably also read F#. So next we've got C#, because the .NET platform was and remains like mainly C# language. So the influence of C# for F# was here also like strong. SCALA is a good example of influencing language for F#, because they show how to put functional programming on top of the platform, which is rather object-oriented. And as well, we have some Python here, because there are some like syntactic sugars taken from Python as well. And some influence from Erlang. The actor model in Erlang, maybe it's not such visible in F#, but there's even a type in base library called mailbox processor, which is supposed to do what the actor model is based upon. Okay, so moving to part 2, I'd like to talk about basics of F#, and I'll talk about general premises, but I'll focus mainly on semantics and syntax of F#. And I've decided to make it side by side with SCALA comparison. So that's because most of you are probably familiar with SCALA, and I thought it's a good idea to do this way. But there was one problem, and I have also my disclaimer. So I don't know a thing about SCALA, but fortunately there are a couple of resources on the web which helped me to compile a few slides. So yeah, these are the slides which I used for my presentation. These are links to resources which I used in my presentation. Okay, so let's first have a look at the general similarities between F# and SCALA. So we can say that they both introduce functional programming on top of an object-oriented platform, and we talk about .NET and JVM respectively. With that regards, they enable interoperability with existing ecosystem, and neither F# nor SCALA are purely functional, which I mentioned before. So yeah, they fall into the category of non-purely functional languages. But they are statically typed, and they have type inference mechanism. I'll talk about type inference in the later course a little bit more, because the type inference mechanism is a bit more rich in F# in comparison to SCALA. And yeah, they both ship with a set of base libraries to use. So yeah. Okay, so let's go to the code. Okay, so as you can see, I have some nice small logos here. There's first for F# and second for SCALA, as you probably know. And first thing I would like to talk is simple bindings, immutable and immutable bindings. And as most of us know, the immutability is one of the main premises in functional programming. And F# wants to emphasize that by showing that you have really to struggle to define a mutable value, because you have to type this mutable keyword here. And it's really, that's like 7 keystrokes more. And you even have a new operator for mutating a value right here. This is not the same like the equal sign. So as you can see, you have to have extra ceremony to make a value mutable in F#, while in SCALA you just have like val and var. This is quite similar. Yeah, by the way, coming back to this disclaimer, I know very little about SCALA, so if I tell something stupid about SCALA, you have all rights to correct me, so please do. Yeah, so that's just one small thing. Similar story to nulls, because if we want to model a value which which may or may not have a corresponding value, we tend to use option type for that, and that looks very pretty similar in F# and Scala. So we have the option type, which is generic. However, in F#, while in Scala you can still use nulls, you can do that in F# because you get a compile time error, and null is a perfectly valid .NET representation of a value. However, compiler enforces you to use option instead of nulls here. There are some tricks to apply to bind a null value to a symbol. However, you need to dive that deep into reflection stuff. So yeah, that's just another small thing. Functions. So yeah, as you can see, the syntax is quite different here, and this is mainly because the F# syntax is influenced by OCaml, as said before. And so we have some small functions like adds, which adds 2 integers, and the function application you don't use parentheses in F#, which you do in Scala. So that's just like a different syntax here. And functions in F# are carried by default here. What that's supposed to mean is that you can apply only one parameter to a function which takes 2, and this gives you another function. You can do that in Scala as well, but from what I've seen, you have to either apply a special signature for that function, or use underscore for carrying using this previously defined add function. So just a little bit more ceremony here. But what's nice about Scala that we don't have in F# is that you can use implicit arguments. For example, if we define a lambda in Scala, we can use like implicit argument from here, just underscore, which stands for the first argument. And in F# we have to specify the arguments explicitly. And also there's this keyword fun. And I've heard rumors that this keyword is here especially because it's fun to program in F#. So you have the fun keyword here. And type inference. So the basic type inference mechanism is rather similar. So we can bind a value to a symbol, be it X or Y or yeah, whatever. So here we have some integers, here we have some string, the same story in Scala. But then F# type inference mechanism goes further, and we don't have to decorate our function with type signature if the compiler is able to infer that from the body of the function. So for example, here we have the add function, which in Scala case I have to explicitly say that my arguments are both of integer type, while in F# it infers from the body of the function. So we have the function add, which is of type int to int. And this is a similar story with lambda functions. You have to be explicit about types when you declare a lambda function in Scala. And the type inference mechanism goes even further in F#, so you can define a function, do it twice, which is a higher order function, and it takes some parameter f, and this operator over here is like the and then in Scala, which says apply this function and then apply the same function. So the type inference mechanism in F# can say that it's a function which takes another function from type A to A and returns a function from A to A. And similar with the and then function here, and who can say what can be the type of this function? And then anyone? Yeah, exactly. So it's a generic function which takes argument f from which is A to B, G is B to C, and the return type is a function from A to C. So the F# compiler was able to infer this type from the definition of the function only. And that's because F# implements the Hindley-Milner type system, which is present in Haskell. And it's very powerful. And the Haskell type system is even more powerful than F#, but I will not dive into this topic today. Okay, so that was type inference. And now a few words about types. Okay, so first I'd like to show the algebraic data types, and first case is sum types. So this means that you can have like a type which can be represented in one of the cases here. So in F# you would use a discriminated union for that. We have a shape type which can be either rectangle or circle with proper backing fields. You can do a similar thing in SCALA. So we have a sealed abstract class, shape, and case classes for that. And pattern matching is quite similar as well. So we can pattern match on values of this of cases of this discriminated union F# and respectively in SCALA. So yeah, the overall conclusion is that the sum types can be represented quite similar in F# and SCALA. There's just a little more ceremony with syntax in SCALA, as you can see, but the whole story is rather similar. And going further to product types, which means just like Cartesian product of two types, so we can create a tuple. In F#, let's say that we want to represent today's meeting, and we can bind to symbol meetup a tuple with value 3 and functional Tricity string. So that's constructing a tuple, which is pretty similar in SCALA as well. And we have pattern matching and extracting values, which work in similar fashion. However, there's this nice syntax in SCALA that you can get by index values of tuples, which you don't get in F#, but you can just write custom functions for extracting values from tuples. And what's also nice in F# that you can pass tuples as arguments of a function, so we can define a function in like a slightly different way that I showed you before, which takes a tuple of arguments, and we can actually call that function invoke with our meetup, with our tuple. And this is also used for interoperability with C#. If we have a method in C# base class, which takes more than one parameter. Okay. Okay, so if we have a function written in C# in base class library, which takes more than one argument, we can invoke that using a tuple for like 2 arguments and 3 for 3 arguments and so on. And on top of tuples, we also get records syntax. So this is like you would have a standard class in SCALA with fields in the constructor. What's nice about records is that you get also a pattern matching for records. You get the labels for values, so you can use the dot notation for extracting values from a record. You get the copy object expression, which just clones the object's meetup, but applies a different value to some of the fields. And you get structural equality for records for free, which I don't think you can have that in SCALA if you don't override these members for equality, but I might be wrong. I'm not sure with that. What's one thing missing in F# with records is the one thing taken from Haskell here, is that if I define record in Haskell, similar to the one in F#. I get functions for extracting values from the record for free. So I can say let G equals group from meetup, and this actually extracts a group property from this record. So that's missing in F#, but it's present in F# in Haskell. Active patterns. This is nice. It's a nice feature in F#, which allows you to define your own custom patterns for pattern matching, which you can do also something similar in Scala. But from what I've learned, you have to create new objects with this unapplying method, which will work in the pattern matching. So again, a little bit more ceremony here. And you can do that like this active pattern in one line here. So this says that it's a pattern which, for n, which is integer, returns either even or odd. So it's one of the cases, nothing else can happen. And here's the syntax for pattern matching in F#. This is, by the way, syntactic sugar for pattern matching in F#. I have more slides with standard syntax for pattern matching in F#. Okay, so active patterns can be extended even more, and we have partial active patterns. For example, we can have an integer partial active pattern which can return integer but may not. So we can try to parse incoming string, and if we succeed, we can return some and otherwise none. And we can use that further for parsing strings. So using regular expressions, we can define a regex match active pattern, which either returns success or failure. When not success, this is a failure, and if it succeeds to find the regular expression in this string, it returns some. And it can be even parameterized by the regex, and it returns the found values here. So if we apply this to the active pattern here, this active pattern in the pattern matching here, you can see I have 3 groups for digits, and this can represent my some format of date, and I can pattern match a list here, and I can be sure that I get 3 integers from here, extracted from this regular expression, which is nice because m, d, and y here are of integer type. Okay, a couple more slides comparing F# to Scala. We've got a nice operator which is called a pipe operator in F#, and it's commonly used for pipelining the pattern, where you get an initial value and you can pipe that to a function which does something with this value, and you can do similar story in Scala, but you have to have these methods defined on this concrete type. So in this example, we have some range which is converted to list, and we have in later course methods which are defined on the list class. And in the F# with this pipe operator, we can apply arbitrary functions. The only restriction is that the last parameter to the function must be the value passed before at the left side of the pipe operator. Yeah, so that's a nice operator commonly used in F# code. And okay, generics. We have drop function here, which takes tail from our list, so it leaves the head and returns only tail. In case the tail list is empty, we throw exception. And as you can tell, the drop function here in F# can infer that that the list parameter is a list generic in type of T. And because the type inference mechanism works here, you don't have to be explicit to tell that it's a list of type of a generic type. Okay, so the generic story is, with regards to code, is quite similar. What's different is that in JVM, the generics are erased after compile time, and in .NET, the generics are in .NET itself, so you can later reason about values from generic structures. So that's nice. However, there's one thing that's missing in F#, and it's if we take a look at map function, we can use mapping for such areas like option value or a list or asynchronous computation. So async is just like a future in a Scala world. And as you can tell, we do quite similar stuff right here. We want just to map the value over here to a function at 5. However, as you probably have noted here, we use 3 different functions. So that's option map for options, lists for list, and async for async stuff. While in, for example, Haskell, you can do that just with fmap function, which is the only one function from the functor type. So the conclusion from that is that there are no higher kind types in F#, and if you want to simulate such computations, you have to define functions and operations on each of these types separately. Okay. And we go now to computation expressions. So this is a feature in F# which allows you to define this kind of monadic bindings, and you can this is an extensible mechanism. So you can define your own builders for such computation expressions, and I've defined here a maybe builder. And this is a popular example with record type person, which can have mother and father, but they are of option types. Okay, they can be still alive, or they can be dead. And we have a function both grandfathers, which is supposed to extract 2 grandfathers of a person. So this is what a computation expression may look like in F#. You get the let bank operator, which is the corresponding bind function in functional programming. So this is what it looks like in F#, and similar story with async. So we get a code which asynchronously fetches some quotes from the web, and then based on some logic applies actions. But so we get the let bank operator here, but as you can tell, we have a different keyword here and here. So this is just like a completely different object. So we have to define separate objects for computation expression for other types. While in Scala, which supports higher kind types, you can do that using the Scala comprehension syntax. So the previously defined function can be written in Scala like that, so you get this for yield syntax. Okay, so that's generally it with regards to comparing F# and Scala on the language syntax and semantics level. Yeah, we get a funny overheard quote here that F# probably isn't a bad language. It's just attached to a bad platform, the opposite of Scala. So yeah, and I have also a different summary for a more general concept between F# and Scala. So we can tell that F# is functional first, so it's really it really encourages you to write your code in functional style, while Scala is, from what I've heard, rather more object-oriented, but it can give you some functional programming features on top of that. So yeah, that's a difference with regards to paradigm. And functional features such as generics or tail calls, which are also present in Scala, but they are only on compiler level, so they like, with regards to generics, they're erased at runtime, and the tail calls are only on compiler level, but on .NET you have that in platform, like baked in, but there's no support for higher kind types, so more experienced functional programming developers might suffer from that in some way. And with regards to the syntax and scopes, it's rather more concise in F#. It's rather strict. You get less options for defining a function or some other computations, while syntax in Scala is rather loose and more verbose, I'd say. And for scopes, F# uses, as you can tell, whitespace. It's whitespace sensitive, so you use indents for declaring scopes, while in Scala you use mainly curly braces still. Yeah, so that's regards syntax. Okay, so now I'd like to show a couple of outstanding F# features. This is the third part of my talk, and I'd like to focus on type providers, on the fact that F# compiler is a one-pass compiler, and units of measure. So type providers is rather an essential feature for F#, and from what I know, there's only one other language called IDRIS, which implements type providers. And what type providers are is we can think of them that if we give them some kind of schema, be it XML, JSON, CSV, whatever, it can provide in compile time a fully fledged type with members for accessing data, so that we can easily consume that data, and it enables for us IDE IntelliSense, and we don't have to worry about parsing at all of these values. So I have a couple of examples for type providers to better show what I mean. For example, we have the JSON type provider, and there's an open weather API available under this URL. And from the code here, you can see that we only have to give an HTTP URI to a sample JSON from the web, and then, okay, let me refresh that. Then we can create a JSON provider from sample type weather, and then load weather from San Francisco, and we get full support from IntelliSense, showing us which properties are present in this JSON, so we can access them. And in the background, this JSON provider makes an HTTP call to this URI here, parses the incoming JSON, and creates a type for that. So we get that for free, which is really nice if you you are like a data scientist. You don't have to write your own parsers for common formats. Similar story with CSV type provider. There's an endpoint for Yahoo Finance stocks, and in this case we have the data on local drive, and we can load data which corresponds to this CSV schema from internet. And in this example here, as you could see, we had the IntelliSense, and we just like get stocks for Facebook quotes, and print 7 newest clothing quotes from 7 last days. Okay, and type providers are an extensible mechanism, so you can use that for any source of data. And here we have word bug data, which is an API which provides you a lot of indicators. So in this example, we can fetch central government debt from United Kingdom and apply some computation on top of that, which is really nice. And as I said, it's an extensible mechanism, and you get really plenty of type providers publicly available on GitHub. And so I've showed you CSV, JSON, worldbyte, but there are type providers for like file system and YAML or SQL clients, some other languages. There's an R language type provider, which is very nice for data scientists because they get all the R language functions baked into the F sharp. So they can use like R functions in F sharp. And yeah, there's really plenty of that, and you can read more on type providers in this presentation here. I'm not sure whether by the way, these slides are publicly available on my site, and I hope they can be shared later on so that you can get the URL for the slides. So you can browse later links and etc. Okay. And next feature, some formatting here happened different. Strange. Okay. One-pass compiler with top-down dependency order. As you can tell, we can use functions defined previously in code. So we can have an add function and use it right here. But if we try to access a function which is defined later in our code, we get a compiler error which says value or constructor sub is not defined. So you cannot use a value which is defined after in your source code, and you cannot use any other value which is defined after your source code. So you have like top-down dependency order, and this applies to a single file as well as your project structure. So this is a screenshot from one of GitHub projects written in F sharp, and as you can see, the files are not ordered by their name. They are ordered by dependency. They are ordered with regards to the dependencies. So, for example, we cannot use in add process source file functions from releases file. And you might think, wait a minute, so why do you think that's a feature? It seems like a limitation that I can't use functions defined later in course, later in my code. But that was my initial thought when I started learning F sharp as well, and I treated this as a negative. But then later it turned out that it actually helped to reason about the code, because I'll tell you one example. Let's imagine that we pull a repository from GitHub, and we want to browse through the code. And how do you tell where's the entry point of a program?
The last file.
Yeah, but when you have order by names.
Well, then you search something on the topmost level that resembles main program, or maybe the name of the project.
Yeah. So that's a little more ceremony here. But if you have the top-down dependency order, you can tell that you have the public API in the last file, which is really nice because you can open that file and you can see what's publicly available, and it really helps to understand code. It's really faster. It helps you faster recognize some patterns here. And if you're still not convinced by what I'm saying, I highly recommend reading Dependency Cycles series by Scott Vlashin. This is a very nice blog for people who want to learn F sharp. And he describes why we should treat this characteristic of F sharp not as a limitation, but rather as a feature. Okay, and last thing from this F sharp unique features is units of measure, and this is as I noted here, only a compile time feature. So we can define an attribute for a type which says that it's a measure. So we can have like measure for kilometers, miles, and hours, and then we can use that in arithmetic computations. So we can define a speed in kilometers per hour or miles per hour, And here we have a couple of values. Two of them are kilometers per hour, and the last one is miles per hour. And while you can sum the first two of them, you cannot sum the first and the third because you get a compile time error for that, which is nice because you probably don't want to combine kilometers with miles before converting from one to the other. And they can also be used in a generic way, so you can decorate a generic type for another type with measure attribute, which means that vector 3D will have 3 coordinates, and all of them are in some measure. And as I said, this is only a compile time feature. They erased in write time. But it helps to write programs which deals with units. And there are some epic software bugs related to units mismatch. One of them is here I'll quote. And 1999, NASA lost 125 million Mars orbiter when a Lockheed Martin engineering team used English units of measurements, while the agency's teams used the metric system for a key spacecraft operation. And yeah, that's one of software bugs which cost a lot, and it could be omitted if you use F# here, units of measure. Okay, and the last part of my presentation today is the evolution of language. And we've got F# software foundation, which is available at this URL, fsharp.org. And as it quotes, its mission is to promote, protect, and advance F# programming language, and to support and facilitate the growth of a diverse and international community F# programmers. So that's what they do. And for example, they have programs of interactive learning. So they have Skype one-to-one pair programming sessions, where one person is an F# guru, which teaches the other person writing in F#. And the other program is that they found speakers around the world to come to your country and speak on your user group. So yeah, that's just 2 examples of what their mission is. So they we can generally say that they aim to promote F# language. But what I'd like to emphasize is that F# is really very community driven as well. As it is open source, there are plenty of contributions to F# core, and from what you can see in this tweet here, the latest F# 4.1 version is a contribution from people from the community. A lot of contributions from the community apart from Microsoft. So that's a nice thing. That's a nice thing. We get plenty of open source projects written in F#, and the community is really great people. They support each other, and it's like a nice F# family. So yeah, I'm glad to be part of it. And what's nice about F# is that it's cross-platform, and even on the fsharp.org site, you get guidelines for starting with F# on Mac OS, on Linux, as well as for iOS and Android. And there's this Ionite package suite for cross-platform F# development, and it includes the Atom editor and Visual Studio Code extensions for F#. So you can use Ionite on Mac or Linux to develop F# programs. And the cross-platform for F# is really a thing, because as I said before, one might think that F#, when in relation with Microsoft, is just limited to Windows, but it's really not, because from what we can tell from the result of F# survey from this year, there are people who mainly use Windows, but also use Mac or Linux for writing F# programs. And while Windows with Visual Studio is still the most frequently used environment for writing F#, we can see here examples of writing code in Atom, Visual Studio Code, MonoDevelop, Vim, even Emacs, Sublime Text, etc. So yeah. And also F# is fully supported on the newest thing from Microsoft called .NET Core, which is a cross-platform platform for writing .NET code. And yeah, F# is fully supported on that as well. And going further to commercial use of F#, so I've extracted a couple of logos for companies that were used in testimonials for F#. And here's our company as well, but we don't use F# in production yet. I try to introduce F# step by step, and we already use F# in our build scripts and for tests. We use F# for property-based testing as well. So we'll see what happens in the future. And what's missing for F# is like still a big success stories like we have for Clojure and Scala or Erlang. But hopefully that will change in the nearest future. There's one example of Jet.com company, which you might have heard of. And in recent news, there's something that's Walmart bought Jet.com for $3 billion in cash, and they aim to fight Amazon. So that might be a new big thing. And Jet.com, its backend is written entirely in F#. And we get a nice tweet here that it would be great if Jet could be for F# what Twitter was for Scala, because as you probably Twitter uses Scala on its backend as well. And okay, one of my last slides, I think that's, yeah. Projects written in F#, so we got a couple of them. These are the most common ones, the most known ones. We get Fake, which is a build automation system written in F#, which is a nice DSL for writing build scripts. We use that as well at our work. Packet for managing dependencies in .NET. F# data, which I showed you with type providers, it provides. It comes with the type providers for best known file formats like CSV, JSON, HTML, and XML. There are some editor extensions like F# Power Tools for Visual Studio and previously mentioned Ionite for cross-platform editing. There's Swath.io, a lightweight web server written in F#, which is really nice. FSCheck for property-based testing, which we use. And others, fparsec, Fable, which is a compiler to JavaScript. So F# has also a compiler to JavaScript, and it goes through Babel. So this is the new thing that uses the transpiling of ECMAScript, the newest standard, to the older ones. And FS Reveal. So this is like a meta project, meta point, because this whole presentation is written in FS Reveal, and I've wrote my slides in Markdown. And you might know the Reveal.js project, which is for creating presentations in HTML and JavaScript. And FS Reveal extends Reveal.js so that you can write your slides in Markdown or as an F# script. And they are like compiled to Reveal.js. And this is a presentation written in FS Reveal. And of course, you can use any .NET project in F#. As you have the full interoperability. Okay, to summarize, we talked about brief history of F#, how it saw the daylight, and what were the origins. We saw some basic stuff regarding general premises, syntax, etc. And I tried to compare that with Scala, but if I told some stupid things about Scala, don't sue me. We saw some outstanding F# features like type providers, the thing about the one-pass compiler, and units of measure. And lastly, we've seen how the language is evolving nowadays. Okay, so that's the summary, and time for questions. Any questions?
Maybe what languages were used to write F-sharp?
F-sharp.
Only F-sharp? There is
I'm
below?
I'm not sure what were the bootstrapping for the first version, but now the compiler and the F-sharp core library are written in F-sharp entirely.
I believe it was actually made in CLR in its early days.
Probably, I don't know that, but for now the status is that it's written entirely in the F-sharp.
Yes.
So you have currently some process of migration to .NET Core because Rosling, for some reason, didn't include it F-sharp.
What's the migration story for .NET Core?
Yeah.
I can't tell you much about that because I don't have much experience, but you can for sure navigate to .NET.com site, which includes examples how to bootstrap F-sharp projects. But there's also a nice. Can we later share some links on the site? I do my best to share link to a GitHub repository which shows you how you can convert an F-sharp project from .NET to .NET Core. So yeah, that's possible. There's a guy Enrico from Italy who's from community. He's not the Microsoft employee, but he's like the man for the .NET Core with F-sharp. So he knows everything about that, and he's got his project on GitHub where he has detailed information about that. Sorry, I can't tell you much about this because I didn't have experience with that.
Is there any way to define new infix operators in the...
Yes, you can define your own infix operators.
To overload existing
Yes, you can overload existing operators. Not sure what about the most basic ones like plus or minus. You cannot probably, but you can extend, you can overload operators which are defined in other libraries. So for example, you can consume a library from GitHub and you can override an operator which is defined over there. But as it's said here, you cannot overload the most basic ones, operators.
So what are the key differences between F-sharp and OCaml?
And OCaml,
Yes.
the underlying platform. Okay. So F-sharp is aimed for .NET, and OCaml, from what I've known, from what I know, is comes with its own runtime.
You don't necessarily run F-sharp in .NET. I think you can also use Mono. Maybe there are some like other targets. So it's like, what are the differences in the language?
Could you?
Because well, you can, of course, you could like for instance create SCALA for .NET or natively compiled.
Mm-hmm.
What are the differences in the language features, so to speak?
Between F-sharp and OCaml.
Yes.
Because
it seems pretty.
Yes, it's very similar. F-sharp comes with a couple more features. I don't think there are type providers in OCaml, for example. So I haven't written a line of code in OCaml, so I cannot tell you much more about it. But I'd suppose that F-sharp originated from being very similar to OCaml and then extended on top of that. So I guess in some point of time, they just live their own lives and yeah. Did that answer your question? Yeah. More or less. It's better than nothing. Okay, any more questions?
There is a tweet related to platforms. I don't want to start a war, but the tweet basically stated that F-sharp chose the wrong platform, kind of. And why, in your opinion, it chose the wrong platform? Like, what is JVM benefits of SCALA? Maybe the guys can answer. Maybe someone is familiar with .NET too, right? Like, kind of. Just answer what is the benefits SCALA got from JVM
Mm-hmm.
that F-sharp didn't get from .NET.
Mm-hmm. It's a tricky question. That's an excellent question, and in my opinion, I think the success story for JVM is that it's used in commercial use more broadly than .NET code. I guess you get the .NET stuff mainly in like banking sectors, etc., while the JVM is ubiquitous in elsewhere. So that's one thing. Maybe also the ecosystem itself, like the managing of packages. I've heard rumors that people tend to prefer Maven or Gradle types of stuff rather than NuGet, which is the package manager for, which is one of the clients of package management for .NET. So this might be the premises of why there are, but that's of course, that's a debate, yeah, whether which one platform is better in which regards. So yeah, that was just.
Type of F# is much shorter than Scala because of the .NET framework than JVM.
Compile time is not shorter than.
Yeah, it's much shorter in F#
than in Scala. Okay.
I was very surprised by this bit because probably we have much less boxing due to generics that you mentioned.
Yes.
Like arrays
Yes.
of things. We have much less mess with primitives like dates,
Mm-hmm.
Java. We have type providers that are from the language itself. So I choose to say don't see how we have packets, of course, instead of nuggets. That was a pretty invalid thing.
Mm-hmm.
for package
So
management. I don't see
that means that you should try F#.
No, I've tried it already a bit, but like I was just surprised by the bit itself.
Mm-hmm.
Yeah.
Okay. Any more questions?
Maybe I'll add something. I think that it's good to mention that one of the biggest open source projects, maybe not written in F#, but which offers the F# API is akka,
Mm-hmm.
AKANet, which is support of the akka from the Scala, and it is production ready in terms of the akka core, remote and clustering. I don't know about streaming and akka HTTP, but the rest is implemented and it works fine. So I think it's good to mention because
Mhm.
the F# API for this is pretty good and
Yeah. So
easy to use.
Eka.net is like the Erlang actor model for this is a port of Eka from Java world, and I haven't used Eka.net, but I've heard that it's pretty well, and it's nice to use for this type of processing and actor model. So yeah.
There is one more question that was questioned, I think, somewhere about what is the difference between OCaml and F#.
Mm-hmm.
And workflows that you mentioned are actually a very, very strong idea
Mm-hmm.
of abstraction over the stuff. I'm just wondering
The
how-
computation expressions, you mean? Okay, you don't get that in OCaml?
I think so.
Mm-hmm.
And as a good example of that, there is a library called Embrace.
Mm-hmm. Yeah.
You know it. And using those expressions, you can say something like, okay, this code should be executed somewhere in the cloud. So I would say cloud, curly bracket, state something with those bin operators, and that stuff, instead of being async or being something else, will be executed against cloud directly with a very good syntax. Just instead of async, you would say cloud, or you would say maybe, or you would say any monadic binding over there. It's just
Yeah, so computation expressions are powerful in this
and
sense that
are
they are an extensible mechanism, which you can define your own methods for use in this computation expression. And you provided a good example of Embrace, which is a really nice library for computing stuff in cloud. But there are more. Okay, no input. Yeah, so that means end of presentation. There are more. There's an interesting project. Sorry for that. Interesting project called Freya, which is a web framework, and it's extending the idea of a web machine. Some of you may probably know that from Erlang. So the web machine is like a decision-free for incoming request, and you're not implementing handlers per se, but you rather say what should happen in each step of this state machine, and you do that with computation expressions in Freya, which is quite nice. So if you're curious about it, I recommend to check it out, because it's really the code base is really interesting, and the project is interesting as well to use. Yeah, so computation expressions, even though the limitation is that there's no support for these higher kind types, we can extend them in different ways, which allows to express more clever ideas.
Freya is spelled F-R-E-Y-A.
F-R-E-Y-A. And if I remember, I try to attach to that to links for the meetup summary. Okay, we're finishing. I think there are more questions, or that means that you cannot have more questions.
No?
Maybe you have one question.
You should do your presentation again.
Okay,
I think for me.
that was a question.
No. Can you,
That was a
can
request.
You repeat all your presentation
Oh,
for me?
okay.
I didn't understand. Anyway.
Okay, so we'll move back to.
Yes? Finish or not?
Try F sharp.
And again.
Okay, maybe we can show you what's the endpoint for this presentation, so you can. Okay, that's for me.
Yes.
Oh, thank you very much. It's theimowski.com/talk functional Tricity F sharp. So you can see this presentation at this URL, and I hope we will add some links to the
Yes.
meetup as well
Yeah.
later.
Yes.
Okay,
No problem.
cool.
Well, thank you.
Thank you.
Thank you very much.